Okay, good morning everybody. So I'm gonna continue with my videos about molecular dynamics. I think this is video number 4. And if you have any comments or feedback, please let me know so I can update probably for our next video what the topics that you want to see or anything. Just let me know. Just to give you a review of what we studied the last time. We tried to calculate the elastic constants, and actually we did it for copper, okay? And we also discussed that using elastic constants, we can find phase transitions like melting. And actually we did here, having elastic constant as function of temperature, we can see that when C11 minus C12 is less than 0, we have a instability, or we have a criteria for having the calculation stability on the crystal. And we found out for copper it's around 1400. Okay, I went into another publications, and then I have this one right here. It's another one, and probably had to increase the size of the presentation. So I found another publication, and this one right here. They also predict that for copper, the temperature is around 1440, and this is really close to our predictions. Okay, they are also using the EAM potential. Okay, right now, probably people are gonna have an idea what's EAM potential, okay, because I haven't gone into that interaction yet. But I did briefly. If you remember when I went into the tree problem, probably had to go back. And also I think was in presentation number 1. Okay. We also got a potential for the tree problem, okay? And I was discussing that why we need a potential, because if we find the gradient of that potential, right here we can find the force, okay? And we need to have the force to do molecular dynamics and probably use a numerical integrator like a Verlet and so on and so forth. So that's the reason why we need a potential. If you want to look more information about this, you can go to video number 1, okay? I also explain briefly some things about potentials that are used in general, okay? But regardless of that, and in a publication that I found online, they this one right here, okay, they predict the melting using the diffusion coefficient, okay. That's actually what I did in my presentation, because if we can go back, when I tried to find the melting for copper, actually I was using the RMS, okay, that's like the root mean displacement, okay, of the atoms. And we can see immediately that when we go into the melting temperature, the RMS goes crazy, it goes up abruptly. And if we find the slope of the RMS, we can find actually the diffusion coefficient. So this is something actually I was doing also to predict the melting of copper. And also they are looking at the radial distribution function. Okay, that's another criteria they're using. And they also give you the same results, okay? So anyways, what I want to discuss today in this video, and that's something really important for everybody, is that once we do our molecular dynamic simulation, okay, something that we have to do is we have to visualize our structure, okay. There are different programs that are online, okay, that people use, and actually here in this slide I'm naming a few of the programs that are commonly used to look at atomic structures. I'm gonna give you, because I have used in the past these programs. Okay, so I have a little bit of experience using them. So I'm gonna go and explain the first one. Gmol is based on, I think it's Java. Okay, and actually that's one of the programs I have on my computer. Actually, I can go here and I can type Gmol, and I can see that I have the program right here. Okay, and it let me visualize structures. This program is more for a small, okay, small systems, okay, and because it's I would not really recommend this because it's running in Java for having to look at millions of thousands of atoms. But it's really good if you are using DFT calculations or ab initio, okay, because on that kind of simulation you know how to use large systems, okay. If you go more than 1,000 atoms using DFT or using ab initio, that's a lot, okay. It's gonna take a lot of memory. So I recommend that program for that kind of simulations. PowerView, okay, as some people, this is for high performance computer, and it's also used for multi-scale. Okay, this is not only used for molecular dynamics, but many people use it, for example, for looking at a continuum, like finite element method, things like that. It can run in computers or clusters, and it can run in many processors. Okay, so that's if you want to visualize millions of atoms. Okay, this is actually I'm gonna write right here for large systems. Okay, so I recommend Vito. That's one of the software that's really popular, and actually you can look it on YouTube. I don't have it on my computer, okay, but it have many. I think they have Python script features, okay, and also it have many features like center symmetry. They have many criteria that people use to look at the structures, commonly common neighborhood, things like that. Okay, Atom I use Atom a lot. Okay, I think the person who got it was from MIT. Okay, and instead it's online. If you can download a program actually. I'm still working. That's the one I had on my computer, and that's the one I have used before, and I had more experience in Atom I was able to look at million atoms using this program, and so this is for the large systems and home use. Okay, for example, here I'm in my office, okay, or I'm in my home. There's a program I use because I can look at millions of atoms, okay, but I don't have to. If I want to look at larger systems like billions, then I'm gonna have some issues. But I use it for home use. It's really good. VMD, that's another popular program that people use. This is more for biosystems. So if you want to look at proteins, molecules, complex systems, okay, VMD the way that you have to go, okay. Actually, we can type it right here probably so you can see. VMD, Visual Molecular Dynamics, that's more for biomolecules. So if you are working with, again, I was saying proteins, cell membranes, things like that, you have to use VMD. This one, the the next one, XCRIS10, that's more for DFT calculations and for looking at the electronic structure. Okay, this one is not for molecular dynamics, okay, because as probably you know, everything that we have discussed right now in our videos is classical molecular dynamics, so we don't look at anything related with the electronic structure of the materials. But it's, yes, I put it here as a references for you to know that we have programs that help you visualize that kind of things. The next one, Vesta, is also for electronic structure. So it's more when you have an quantum mechanics. Actually, it's more for quantum mechanics calculations. And then the last option, that's something that I also have used because sometimes one of the programs that we have is not good for us. Then you can make your own program, okay? So you can use like C++, Visual Java, or you can use, and that's something I have used before, OpenGL. I mean, that's one of the really good libraries that you have for running graphicals, intensive graphics that you want to do. You can use it with C++, and actually the problem that I discussed before, the tributary problem in port number 1, actually that was using OpenGL, okay? So using that I was actually able to look like a visual program to look at the movement of the 3 bodies in space, okay? So you can also try to do your program, okay? And sometimes you have to do your programs for looking at the structure of atoms. But honestly, if they ask me right now to like a program to look at atomic structures, I wouldn't do it because it really takes a lot of time, and I'm not in this anymore, so I don't have to do it. Okay, that would be like useless for me, and that would be for specific things that we have to do. But anyways, it's good to know this. Now, when we are also something that we have to consider. Okay, so this is the program that we have to visualize our molecular dynamic runs. Sometimes you have to make your own crystal structure. Okay, and for example, in my case, I make my own program that I use for creating like BCC structure, FCC structures. I also have some feature for making an option number 5 to making nanoparticles. Okay, you can also rotate the lattice. It have many features. Okay, and that's the one that I actually use the majority of the time to create my structures. So let's give it a try just to give you an idea how we visualize the structure. So I can go probably into our oh my god, everyone is looking at my so let's go into documents, and then probably I can go into my program. Okay, so let's try something easy. Let's say that I want to make a BCC lattice, so I can type option number 1. Then I'm gonna put the lattice constant is 3.04. I'm gonna do a 1 crystal structure. Then I'm gonna put tantalum. That's a BCC structure and atomic mass, because I already remember it's 181. So here I can go and look at my structure, okay, and I have 9 atoms, and then I want to save this, so I can go into option number 9, and I have it to have it as an output when AB init. That's more for quantum mechanics. I don't use it, but I put that option there. I also hire for an output for LAMP format, and the one I'm gonna use right now is the XYZ format. Okay, so I'm gonna put option number A. Then I'm gonna write the name of the output file as tantalum, and then we have the XYZ coordinates. I'm gonna write like that. Then I'm gonna exit. Okay, then I can go into Gmod. Then I'm gonna select my structure right here. So I go into tantalum, and actually we can have it right here. It's a BCC structure, and it have 9 arms. Okay. I can try something harder. Okay, and that's something that I have done in the past. Let's make a nanoparticle. So I'm gonna go into option number 5. Okay, and then I'm gonna make a icosahedron. Okay, that's a nanoparticle that have icosahedron structures. I'm gonna type option number D. Then I'm gonna put the lattice like 2.663, any number I want. Okay, I'm gonna put gold. Okay, the atomic mass I don't remember. I'm gonna write 1 as atomic mass, and then I'm gonna put I want a system of 4 atoms. I'm gonna put 4. So I create my lattice right here, and then I can look at my structure. Okay, it has 659 atoms. I can also look for reference if sometimes we don't have overlapping. And I want to save this. I'm gonna go into option number 9. Okay, probably I wanna put for XYZ format. I'm gonna put AO nano. Okay, and then I'm gonna exit. But I'm not gonna exit. I'm gonna open another window right here. Okay, and then I'm gonna try to go into a folder. Okay, and then I'm gonna run Gmod, and I'm gonna open my file. This is the one AU nano, and I have it right here. So this is a icosahedron. Okay, you can see right here it has gold. Now let's see that, for example, I want to add some defects. Okay, so let's say that I want to also add like silver, another metal. So I can go into option number 13. Okay, then I'm gonna replace some of the atoms I have in the structures, and I go and click option number B. I want 50% of the atoms to be silver, and I'm gonna put a G. Atomic mass I'm gonna put 2, and then I'm gonna replace my first structure. Okay, so I can see that I already have this new structure right here. So I can go and I can write it down. So I'm gonna write down as XYZ. I'm gonna put AO nano again, XYZ. And I can go into Gmod. And I have it right here. Let's open it, cross fingers. So there we have. So here we have our nanostructure. It's made of silver and gold. Okay, so half the atoms are silver and half the atoms are gold. Okay, so this is the way that you do it. So yeah, sometimes you have to make your own programs to make like structures. So it's an example. Okay, and I have really application because once you make your structure, you have to visualize it. So the reason why I go back to all these programs that we can use for molecular dynamics calculations. And then I want to refer to the following. When you are trying to visualize the atomic structures, you have to remember that molecular dynamics can be really expensive, and we have to consider the memory that we have on a computer, because actually I once tried to look like 10 million atoms. 10 million, that's a lot. I mean, that's only something that you can do with classical molecular dynamics. And then I was saying, oh, it's because I need a more expensive graphical card or whatever. No, sometimes what happens is that you have to have RAM memory system. And just to give you an idea was that if we only store, okay, the coordinate of each atom, and that will be like an XYZ if we consider it in 3D, okay? And if we consider that each number is in single precision floating point number, it means that it occupies around 8 bytes of memory. Then if my computer has 64 gigabytes of RAM, okay, I will be able only to look at, and that's a lot, 2666 million of atoms. Okay, actually I refrain that because if I can go into my computer, okay, actually right here I can see it. My computer has 64 gigabytes of memory. Okay, So the best I can do when I look at the atomic system, it will be this. It will be like 2666 million atoms, and that will be like a lot because remember that when you're running a program, you are using memory for many things on a computer, so I will be the number of atoms I can visualize it will be less. For example, if I want to look at 5 million atoms, yes, I will require around 12 gigabytes of RAM. Okay, so that give you an idea. Okay, if the more atoms I want to look, the more RAM memory I need, and this is only the minimal amount of RAM that you need, because if you also want to plot like the colors and the other things that, I mean, the potential energy, the temperature, and other stuff that you also want to visualize in your programs, okay, it means that you will need more memory than 12 gigabytes of RAM. Okay, but at least that's the amount of memory that you will need to look at the simulations. So yeah, this was a consideration. I want to explain this to people because sometimes we try to run large systems and we don't have an idea of how much memory we need. Okay, and that's something that you have to know how much memory you need to run your simulations. Okay, now what is the advantage of what we want to look as atoms? Okay, sometimes when we do it on a computer, right, we can visualize in real time what's happening in the structure. Okay, something that is not always possible to do with electron microscopy or X-rays. Okay, so that's one of the advantages of molecular dynamics. You can actually look what's happening around in a computer. Okay, and you can see things in real time without having to go into spectroscopy techniques. Also, another one is you don't have to do experiment, because you know that I was saying before, experiments are more expensive. Okay, so we can predict what's going to happen. For example, if we have a phase transition, when you are compressing a material and you want to see how it changes the crystal structure, if we can do molecular dynamics and actually see what's happening, how the atoms are moving. Okay, well, at least we had an idea before we go into the experiments. Also, for example, if you want to go into fractured mechanics, okay, and that's something I want to discuss in this video. You can also see how the materials break when you apply any stress, or when you apply when you stretch the material. You can also look at that. Also, transfer phenomena. Transfer phenomena will be more like if you have, for example, proteins passing through a membrane. Okay, you can consider like a transfer phenomena, so we can look that on using molecular dynamics simulations. So that's one advantage. The only problem that we have, and that's one where here, however, experiments will always be needed to collaborate findings. I mean, or we had to do experiments. Okay, but at least molecular dynamics give an advantage that it's less expensive. Okay, and it give you like a prediction. So at least we're good. When you're writing molecular dynamics, and that's something that is used because I have my structure, I visualize it using my program like AtomEye or Vito or whatever you want to do, or whatever you want to use. Then I had to use like a color map. And color maps I use for everything. Okay, so for example, if you want to plot the atom using like centrosymmetry parameter, common error analysis, probably you want to plot atoms based on the temperature that they have, or probably you want to plot atoms using like the stress per atom. Then color maps are gonna be useful. Okay, so you can say, red is really hot, and blue is really cold. So if you see that some atoms are red, that means that more temperature, or that region space is more hotter. Okay, so you have a high temperature, you have to look at atoms that they are red. Okay, and you can look at the atoms who are blue. Okay, they are cold. Okay, so that's the reason why we use color maps. And I'm gonna give an example right now of a simulation, and I use this one just to give you an idea how to visualize nanostructures, and also because I wanted to discuss when to use periodic boundary conditions and where not, and not when to use periodic boundary conditions. So the example I'm gonna explain right now is face-centered cubic 110 wires with a rhombic cross section. Probably for people who have no idea what this is, a nanowire. Okay, you grab an FCC structure, okay, and then you do a rotation the system, okay, to make the arms orient to the 110 plane. Probably this is more complex, okay, and then you cut. Okay, you cut the system so you can have the cross section as rhombic. Okay, so that's the kind of system I'm going to discuss right now. And actually going to discuss the stretching. Okay, just to give you an idea, and probably I'm going to exit this program. Probably can go to my. Let me go to my system right here. Just give you an idea. I'm gonna use Atom so you can see the structure. Probably it's working right now. Okay, so this is a nanowire. Okay, so I can probably increase the size. And this is a nanowire is have a. We can rotate this one. This is a rhombic cross section. Okay. Actually, we can actually zoom it. We can go and increase the size. Like we can try and increase and go deeper. Okay. And what we're gonna do in this simulation, I'm gonna try to stretch. I'm gonna try to apply and stress. I'm gonna try to apply a displacement at one of the ends, and then we're gonna observe how this fractures. Okay, and that's gonna be a simulation for today. How I do a simulation? I'm gonna go into the script for everybody who wants to use it using lamps. How I do it? Well, typically you had to have a temperature. Okay, in this case we're using 1 Kelvin because actually I don't care about the effect that happen without a temperature. That's why I'm using a temperature that's really low, close to 0. But here's what I want to discuss. I have regions right here. Okay, so I can see that I have my sample. Then I have one of the ends is gonna be fixed, and then we have another end. And on the other end, we're gonna give a displacement, okay? And then we have the end number 1, okay? We have the end number 2, and then we have the mirror, okay? So we have to divide, and we have to define regions on the sample, right? And then we can create groups using lamps. Then here I define my interatomic potential, and then I can do an equilibration. I want to explain this to you. Can I use MPT or MBT in this system? Yes and no. Okay. I can use periodic boundary conditions, but it's not gonna be. I don't think that's accurate because this is not something that is a crystal structure. This is more like a molecule. This is more like a nanocluster. Okay, so it will not be good to use periodic boundary conditions on all the on all the computational bugs. I have seen simulations online. Some people, for example, they simulate carbon nanotubes. Okay, for carbon nanotubes, probably you can use periodic boundary conditions on the, for example, if you have a carbon nanotube that's extending in the x direction, probably you can use it because if we have a cylindrical shape, okay, you can have like, okay, that cylindrical shapes continues forever in the x direction, so probably in that direction I can use periodic boundary conditions. And probably for this nanowire I could also use periodic boundary conditions in the x directions, But right now I'm not gonna use periodic boundary conditions, but I'm gonna run this on the NVE, okay? And the first thing that we had to do is equilibration, okay? To do equilibration, and actually it should be done using NVE, the microcanonical. I'm using NPT, but because I'm making all the models periodic, but I don't think that's right. What I will do to equilibrate this right, I will run this on the first. I will assign the velocities of all the atoms close to 300 Kelvin, okay, and then I will run a simulation in a microcanonical for some time steps. Probably I can use a thermostat to remove the fluctuations on the temperature, and after that then I can run a simulation, okay. If we go continue, okay, we see that when we do the deformation, I change the boundary conditions so they are no longer periodic, okay. And this is the tricky part for some people. I only apply the microcanonical to the mirror part, okay. I don't have to apply the microcanonical, or I don't have to look at the movement atoms on one of the ends, because that end is going to be fixed, okay. So it's going to be fixed. I don't have to actually do any dynamics because it's fixed, okay. Then and the other end, okay, and that end I'm gonna apply a displacement. That's the reason why I use this command that's called move, okay. So this is what happens. I have my nanowire, or I have my crystal structure, and then I apply a little bit of movement at one of the ends of the atoms, okay. And then when I apply that little bit of displacement, I run in the microcanonical so I can let the atoms to adjust. And then again I give it another small displacement, and then again I run in the microcanonical and I let the atoms to update the velocities, okay, and the displacements, and then again I run in I do another displacement, so that way I can actually control the deformation, okay. And that can you do it in labs using the move displacement, okay. You can also do it by applying a deformation to the computational bugs, but that will be only useful when you are applying periodic boundary conditions. Probably going to explain that to the end. And on that one, you can use the MVT, or you can use the MPT. And actually, I remember a friend who told me before how you can use MVT to compress or to stretch a material, because in the MVT the volume is fixed, okay. So if you are actually stretching a material or you're compressing a material, you're changing the volume. What happened is the following, and this is the tricky part. When you have your computational box, okay, you change the size of the computational box a little bit, okay, and then once you change it, then you run them and you run on the MVT, okay. So when you are running the MVT, the volume is actually fixed, okay, and then again you give it another displacement, a little bit of displacement, and then you run again the MVT, okay. So everything that you're running actually is in equilibrium, okay, regardless that you are compressing slowly the solid, or probably stretching the solid, okay. So there are reasons why you can do it, okay. So yes, and that's actually what I'm doing right here to apply the deformation to the nanowire right here, okay. We're working the displacement of the computational box, or we working the displacement of the atoms, okay. So we give a little displacement, and then we run again in the microcanonical, or we run again in the canonical, and then we can then calculate the new forces and do a simulation. Then if I go here, okay, I can plot the stress, the length of the computational box, and here I'm running to plot my atoms. So using atom I want to have the potential energy, the common neighborhood analysis, and also you can look it right here when we're going to compute. Okay, some compute the lamps use, okay, you can use it here to visualize your structure. And once we run that, then we have simulation. So I'm gonna go here and probably show you what we got. So I have here my script. I'm gonna increase the size of this. Then I'm gonna put the background black because I black, and I'm gonna run it. So I give a displacement at one of the ends, and then you can see how the nanowire is actually stretching. This is done in the microcanonical. I'm not using periodic boundary condition, and you can actually see how the nanowire is deforming. Okay, and we can continue running this. Okay, and actually we continue, this is gonna break. Okay, actually it's breaking right here. It's breaking, it's finally breaking, that's good. Maybe I had to read this, I don't want to look at that. And then finally it's breaking. Okay, and the simulation starts right here. You can actually, depending, I mean, you can control the strain rate, and that's something I'm going to discuss in another PowerPoint presentation. No, I mean the next slide. But I want to look at something right here that's really neat about this structure. And that's something I wanted for you to look. These nanowires, okay, they change from Rabbit, they change to FCC. Okay, that's something, and even I'm really happy because even having this nanowire, because this nanowire is huge, okay? More likely this is not something that you're gonna see in real life, because these nanowires are the one that have more stability, okay? But also have to remember that if you want to make a nanowire that's 10 million atoms, okay, that's really huge, okay? You're not gonna be able to make that in real life, because there's like that's what's called this nano. Okay, nano because it's in the nano scale. So if you continue making it bigger and bigger, instead of being a nanoparticle, it's gonna be a bulk. It's gonna be a crystal. Okay, so but I want you to know that even having this size, okay, and you can see right here how this structure become an FCC structure. You can actually see how the atoms are moving, okay? Actually, right here in the start, right here, guys, this is an FCC structure. And I can tell you that, I mean, I have already run simulations, and this is an FCC structure completely. They have a reorientation, okay, when you apply an stretching. Also, let me go into my presentation. Okay, so how we can define a strain? Okay, so let's for example say that I have a strain, and this is really fast. I mean, when you learn molecular dynamics, remember that you're working in the picoseconds time scale. So if you want to do the formation of 1% each picoseconds, okay, then how much is the velocity you have to kill at the end? When if you know the initial length of your nanowire, okay, and you know the strain rate, then for example in this case this nanowire is 100 angstroms, and I want to apply a strain rate of 1%, then I had to multiply 100 by 0.01, then I had to apply a displacement of 1 angstroms each picosecond. So I had to make the end of the nanowire to move 1 angstrom each picoseconds. Now you have to consider this. If you do this really fast, okay, so you have to consider, if you do this really fast, if you want to move one of the ends and you want to move it 5 angstroms, that's not gonna work, because if you do it, if you're stretching too far away, the one at the end, you're not gonna have enough time for the arms to be next close to the end to equilibrate or to normalize on the microcanonical. Okay, so you're not able to play like crazy displacement. Okay, it has to be a small displacement on the arms. Okay, don't go crazy on that, because if you go large reformation, it's not gonna work. Okay. Then based on that, if I want to deform a nanowire 40%, I will be around 40 picoseconds, or it's gonna be 8,000 steps we consider that 1 time step is equal to 0.005 picoseconds. So this gives you an idea of how many time steps you need to run to actually do simulation. I want to continue, and I want to show you the same simulation I showed you before, but here I'm using a color map. Okay, and actually using a color map, you can see that it's more clearly to see or look at the defects. Okay, and you can see that everything turns green. Okay, it means that it becomes a FCT crystal. Okay, you can really use different color maps to visualize your structure. Okay, also I have the one right here, the same one, but I don't use any color maps to look at atoms. You can see right here. There we go. And I'm gonna start right here the presentation. This is a problem, and this is something really interesting, but there are different ways to do it. Just to go here, and I'm gonna show you if you want to do it, because I also have one. I'm using periodic boundary conditions. So you're gonna go into no, right here. Going to you can also try and go down and do a deformation. So here right now I'm using, this is a command that we use on labs that's called fix deform. Okay, you can also use that, but for using that you are actually you are actually moving the computational box. I would not recommend using that in this scenario because that's not periodic structures. Okay, but you can try it anyways. Okay, and that's the tricky part when I'm using the MVT, and I use the MVT because I have my volume, then I compress, so I stretch a little bit, so I do a little displacement in the computational box, so the atoms are gonna update, and then I run it again, and then I continue and do it like that. So how I do it, and how I do the simulation. Okay. Okay, I'm back. So I'm gonna show another simulation, but in this case, I'm gonna go and put it here so you can see it. So here I have another nanowire, right? But right now I'm gonna deform it by using the computational box. Okay. In this case, I'm using periodic boundary conditions. I will not really recommend periodic boundary condition for nanostructures, but we can say that this cross-sectional area, okay? So in this case, for this length, we can see that this length is periodic, so in this case we can apply it, so I can actually run the simulation. And here I'm actually stretching the computational box. You can see how the computational box is actually changing its volume, okay? And I can see the stretching, okay? And I can look at the information. I would not really recommend this for this kind of structures, okay? That would be more like crystals like copper, tantalum, sodium chloride, who are periodic in all directions, okay? But anyway, we can see the simulation right here. In case that you want to look at how to do this simulation using the, oh my goodness. Okay, in case that you want more information, actually I'm gonna refer to my previous work, but anyway, I'm using like YouTube for making an announcement on my things I have done. But anyways, if you want to have more information, this article right here, a beginner guide to the model of uniaxial quasi-entropic compression, and so on and so forward. Actually, I give you here in the script that actually use the formation of the computational box. Okay, in this case we can do it because actually it's FCC and FCC copper. So actually here we can use the fix deform. Okay, in this case we can use the fix deform right here. We can actually use that to do it, and actually here at the end I show a sample of how to look at the defects. Okay, using the same. So this is if you want to look at this, please go into this publication to have more references on how to do it, okay? And some people ask me again, how you can do it if you're running an MVT? If you're running an MVT, if you have the volume as constant, how you can deform the computational box? I already told you, you do a displacement and then you run in the MVT and hour, and then you run. So everything is in equilibrium at the end, okay? And also you can do the simulation using the MPT, okay? In the MPT, the volume isn't going to be fixed. And actually, I'm going to show you, well, probably in the next simulation, I'm going to show you this. In the next video, I'm going to show you what happens if you're using MPT. In the MPT, the only difference is just the volume, well, actually the volume is changing, okay? But if you're using the MPT, more likely the volume on the lateral faces can also change, okay? Because when you're running the MPT, only the volume on the cross-sectional area is the only one who's changing. Okay, you're not changing the volume on the lateral areas, okay? But I think that's the only difference. There's another, oh, you're looking on Facebook now, looking on Facebook. People make me the comment, and actually that's one of the videos I have in my channel. I'm gonna look it right here. And this one right here, actually, we can look it right here. This is one of the simulations that I'm done before in the past. So actually here, instead of stretching, I'm actually doing a bending of the nanowire. Actually, I'm doing this, I'm doing a bending, okay? I can come on, you can see it. Oh my goodness. So actually here I'm doing a bending, okay? So how we do this, okay? The only difference is that well, we had this video right here, and I can go back to my script probably. Let me go back to my script. Let's try this one. The only difference is that right here at the end, okay, at the end, we can do a displacement. Instead of having a displacement on the X, we can have a displacement, down like this, okay? Or actually we can, in one of the ends, we can apply a force is going down, okay? We can apply a force, and then that's gonna do the nanowire to bending. So there are many ways to do this kind of simulations because it depends of many things. I mean, you can apply like a stretching, or you can apply a bending, okay, or depending how fast you do it, okay. So there are many criteria when you're running simulations to understand it. But anyways, I'm gonna start the video right here. If you have any comments, please let me know, okay. And I think that on the next video, I finally gonna go into potentials, okay. I'm gonna explain a little bit about how interatomic potential, which one are good, which one are bad, okay. And we're gonna do for the next video. Thank you. Have a nice day.